Welcome back to Journeys to the Ice, the podcast of the Antarctic Research Centre. I'm Matthew Wood. Antarctica is uniquely located on the globe as a continent surrounded by a single ocean. In this episode, we take a look at the Southern Ocean and its relationship with Antarctic climate. With bitterly cold waters, seemingly endless expanses of sea ice, relentless currents and wandering icebergs, the Southern Ocean is a formidable enough place today, let alone at the height of the last ice age. Lionel Carter is Professor of Marine Geology at the Antarctic Research Centre, where much of his work is focused on improving the understanding of how Antarctic climate affects both global ocean circulation and the water masses of the New Zealand region. Hi Lionel, welcome to Journeys to the Ice. Today's topic is Antarctica and the Southern Ocean. To begin with, could you briefly describe the Southern Ocean and how it fits into global ocean circulation?
If you're asked to describe the Southern Ocean first up, it's cold and it's pretty turbulent. To come to grips with the Southern Ocean, you've really got to think in terms of a current system called the Antarctic Circumpolar Current. And it really is a current of superlatives. It's the world's longest current, 24,000 kilometers. It's the world's largest current. Is wind-driven, in other words, the winds force the water along, to the extent that about 40% of the wind energy falling on the planet is accommodated by the Antarctic Circumpolar Current. It is a big feature, and basically it covers most of the Southern Ocean. The current flows from west to east, and it's the only current that connects all the major ocean basins. It connects the Pacific, the Indian, and the Atlantic. And so it's a key ingredient for mixing the waters between those major ocean basins. It really is the big connector.
And what about 20,000 years ago at the height of the last ice age? What were Antarctica and the Southern Ocean like then?
It certainly was a lot colder, and the ice shelves in the Weddell Sea and the Ross Sea, they were no longer shelves. Currently, they have water underneath them. In the Ice Age, basically, the ice extended so that the ice shelf became an ice sheet and that the ice grounded on the seabed, and that extended forward to the continental shelf. We all know that Antarctica doubles its size in winter due to the growth of sea ice. Well, in the Ice Age, that sea ice was far more extensive, and it was extending to latitudes of 60 degrees south and perhaps even further north.
So this sea ice didn't quite reach New Zealand, but in your work, you've shown that at these latitudes, sea surface temperatures were greatly reduced, around 4 to 6 degrees Celsius lower than the present day. How do you go about reconstructing these temperature records?
To determine how the ocean was about 18,000 years ago, we really go into basically forensic science. And for that, we rely primarily on cores of sediment, tubes of mud taken from the seabed. Within that mud, there's microfossils, very small fossils that are the remains of plankton. Now, when these plankton were living, their shells grew, and their shells incorporated isotopes that are in the water, the isotopes of oxygen, the isotopes of carbon. They also incorporated elements like magnesium and calcium. The plankton died, they fell to the seabed and produced a layer, and that process has continued through time. So when we get our sediment core, we go back through the layers, we can date them and say, well, that horizon's 18,000 years ago. What was the ocean like then? We then take the plankton apart. We can measure these isotopes of oxygen and carbon. We could look at the ratio of magnesium and calcium. So by looking at these chemical proxies in the ocean, we can reconstruct not only the temperatures of the ocean surface, but in the case of the isotopes, we can get an idea of the amount of ice that was being stored in Antarctica and, of course, in the northern polar regions.
So in the present day, the Antarctic Circumpolar Current is driven by these westerly winds that blow across the Southern Ocean and is ultimately steered by the topography of those deep ocean basins. But during glacial maximums, the northward migration of ocean fronts must have pushed the Antarctic Circumpolar Current into the southern hemisphere continental land masses.
That's our belief, at least in two areas. In the Drake Passage in New Zealand, the Antarctic Circumpolar Current is strongly constrained by the seabed topography. The one thing about the circumpolar current which makes it truly remarkable is that even though it's windblown, it is moving from top to bottom. The wind is just not moving the surface ocean, but moving the deep ocean. And that effect goes down to at least 4 kilometres water depth. Now, if you're moving the front northwards, it essentially moves against this topography. And it's like a rock in a river. You notice when the rock projects into the river that the river flows fastest around that rock. And that's the case in the ocean. The Antarctic circumpolar current, it migrated northwards, it's impinging against the submarine landmass of New Zealand, and it intensified.
You mentioned the Drake Passage, that gap between the southernmost tip of South America and the Antarctic Peninsula. The Southern Ocean is only about 1,000 kilometers wide at this point, so that must make for some pretty interesting circulation.
Well, basically, you're trying to squeeze the world's largest current through the eye of a needle. When you start to squeeze or constrain the current, it speeds up. And so the flow through the Drake Passage is enormous. And we all know the stories of sailing round Cape Horn. Well, part of that turbulent ocean is a result of this constriction, as well as the abominable weather. When it goes through the passage and it comes out on the eastern side, it starts to ride northwards. And so the current rides up against the Falkland Plateau. In New Zealand, it rides up against the Campbell Plateau before it peels off and it continues its west to east journey.
When we talk about the differences between the ice ages and the present day, we're really talking about large-scale natural climate variability driven by variations in the Earth's orbital parameters. But climate can also change at millennial, suborbital timescales, and there was this event called the Antarctic cold reversal. When was this event and how localized was its influence? For example, does it show up in climate records from the New Zealand region?
When we look at New Zealand on a map, it's quite clear that we have sort of two drivers. One is the subtropics and one is the subantarctic or the Antarctic polar regions. So part of the southern island sits in the Southern Ocean and the remainder of New Zealand sits in the subtropical Southwest Pacific. Now, between 14 and 12,500 years ago, Antarctica unexpectedly went into a cold phase. At that time, we were just coming out of the last glacial maximum and climate was generally warming. Off New Zealand, we see an immediate response in the South Island, both in the surface waters and the deep waters. They both started to cool by as much as 1 degree, which doesn't sound much, but when you look at that as an average, it's quite a marked change, which was in phase with what was happening in Antarctica. When you go to the North Island, quite a different story. In the surface ocean, we didn't get cold until about 600 years after the Antarctic cold reversal began its cooling in Antarctica. And the reason for that is we were getting at that time a strengthened inflow of warm subtropical water, and that blunted the effects of the Antarctic cold reversal. The surface waters coming in from the subtropics were only affecting the upper ocean. In the deep ocean, though, we had quite a different response. The deep ocean was very much controlled from Antarctica. When we look around in the South Atlantic and parts of the Southern Indian Ocean, we see the same response. If you're in the subantarctic waters, you get an immediate response to the Antarctic cold reversal, and it's working in phase with what is happening in Antarctica. When you go north, you get this subtropical influence, which tends to ameliorate that cold reversal response.
A more recent event in the Southern Ocean that many listeners of this podcast will remember was, of course, the dramatic arrival of the icebergs off the southeast coast of New Zealand in 2006. Considering the human and geological record of icebergs, was this event anything out of the ordinary?
There's nothing new about icebergs coming to New Zealand. When you look at observations from old sailing ships, from merchant ships, a little later in the very late 19th century and into the 20th century, icebergs are a common feature of our seascape. We had an iceberg around Dunedin in 1938, for example. We know when we look in the geological past, we know that during the ice ages, we have icebergs breaking off from Antarctica. If the ice has been sitting on the seabed or sitting on rock, as that ice moves, it incorporates grains of sediment, lumps of rock into its base, and it's frozen there. Once that iceberg breaks off, it starts to float. It comes to New Zealand. These guys arrive here in large numbers. There's not much melting en route. And thereupon meeting warmer waters, it starts to melt and it drops those telltale debris, and that's incorporated in the sediments. When we look on the top of Chatham Rise, some of them have been so large that they've actually scoured the top of the rise. The icebergs have reached subtropical water, and so the top of Chatham Rise is basically an iceberg graveyard.
So the icebergs of 2006, by themselves, don't necessarily imply anything about global warming.
It's a sign, but because we see icebergs coming to New Zealand throughout our geological records, it's nothing novel. We'd like to see a longer term record. However, we may not have time to wait for that record to come along. Now, when we look at these straight observations of ocean temperatures and ocean heat content into the Southern Ocean, indeed it is getting warmer. And significantly, it's getting warmer to depth. So at about 700 to 1,000 metres, the ocean has warmed up about 0.17 of a degree. Now that doesn't sound like much, but when you extrapolate that over the entire Southern Ocean, that is a lot of heat, and the ocean's always reluctant to release that heat. So in essence, the warming effects that we see today are with us for a few centuries, even if we cut emissions to zero.
So it sounds like there's a need now more than ever to understand the interactions between Antarctica and the Southern Ocean. Is there a large knowledge gap that needs to be filled?
When you look at the North Atlantic, if you look at oceanographic stations, seismic lines, coring sites, it is totally peppered. And the reason for that is quite obvious. A lot of people live around the North Atlantic, and the same applies to the North Pacific Ocean. And so the research has tended to focus on those areas, understandably so. It's only been in the last 20 years that a lot of effort has started to come south of the equator. That research is starting to show that Antarctica is one of the big drivers of the ocean, and I'm talking about the world ocean here. What are the key questions? Well, how does the Southern Ocean operate? We're starting to get a handle of that, particularly as the bigger physical oceanographic programs come to fruition. The World Ocean Circulation Experiment, which was completed a few years ago, is starting to show how that Southern Ocean operates. So there's a lot to learn. Importantly, the role of the Southern Ocean in controlling climate has really come to the fore because the Southern Ocean is a major sink of carbon dioxide. Plankton take up carbon, the plankton sink and remove that carbon from the system. We also have very strong mixing of the system simply because we have strong winds down there that mixes CO2 into the surface waters. So there's quite a strong regulation of the carbon dioxide budget. Research that's coming out is saying that at the moment, the Southern Ocean, because it's warming, it's reached its limit of taking up carbon dioxide. And research is going on to confirm how valid that hypothesis is. But there's no doubt that it does have a major influence on the global ocean circulation and the atmosphere.
Lionel Carter, thanks very much.
Thank you.
For more journeys to the ice, visit sciblogs.co.nz/Journeys to the Ice.